Welcome to another Royal Astronomical Society's online public talk. Hello, I am Lucinda Offer, Education Outreach and Bicentenary Events Officer for our 200th anniversary of the Royal Astronomical Society. Our organization advocates for astronomy, geophysics, and space science in the UK since 1820. I am excited to introduce to you today our bicentenary talk guest speaker, Dr. Tana Joseph, who will speak with us about the SKA Square Kilometre Array project and showcase some of its groundbreaking results that is building research capabilities in Africa and the broader impact it is making, from improving schools in rural South Africa to cutting-edge data-intensive facilities. Dr. Tana Joseph is a South African astronomer, science communicator, and entrepreneur currently based in the UK. Her area of research is black holes and neutron stars and binary stellar systems outside our own Milky Way galaxy. She earned her PhD at the University of Southampton and has worked as a researcher, outreach astronomer, and held both Fulbright and Royal Society fellowships. A quick reminder that there will be a Q&A after her talk, so please get your questions ready. There are places to post your questions for our speaker if you've joined us on Zoom in the Q&A box and on YouTube in the chat box. Thank you, Dr. Joseph, for being with us today. And to celebrate our 200 years of the Royal Astronomical Society, on to you.
Hello, everyone, and thank you for joining me this evening. I'm very happy to be here with you all, and I hope you enjoy my talk. So let's get to it. So I'll be talking about changing perceptions of what Africa is and what Africa can do, and how the Square Kilometre Array has brought this about. I just want to also make a quick note that for those of you who perhaps tuned in because you wanted to hear about the critical theory framework about Afro-pessimism, that's not what I am using the phrase for this evening. I apologize for the confusion. And I will probably change the name of this talk as a consequence of that. So this idea, or my idea of what Afro-pessimism is just this pervasive sort of general idea that Africa is a place of lack, a place of not many resources in terms of what people can do, a lot of natural resources, but not a lot of resources in terms of what people are capable of, etc. And this was really brought home to me, and the inspiration for this talk was found in a YouTube comment on a video that was posted by the South African Astronomical Observatory, which is also celebrating its 200-year anniversary this year. And the video was about the Southern African Large Telescope, which is the biggest optical telescope in the Southern Hemisphere. And someone basically wrote and said that they didn't know there were such big telescopes and so many astronomers in South Africa, and they were surprised because it's Africa, and they wondered about who is funding them and how come an African country has funding for science. And that really just brings home this idea that people outside Africa looking in have a very narrowly defined idea of what the continent is. They tend to think it's one country instead of 54 very different countries, with an enormous wealth of cultural, linguistic, and biodiversity, just to name a few. So in this talk, I'm going to talk about the Square Kilometre Array and how it is bringing about all this positive change on the continent by ushering in an era of cutting-edge technology and science. So start with, I asked the question, and I'll ask this question throughout the talk: what is the Square Kilometre Array? What is SKA? And the short answer is that it's the world's best radio telescope. So here on the left, we see the continent of Africa with its countries delineated, and you see all these dots, these white dots and the yellow dots. That is where the one part of the SKA will be built across Africa. And then on the right-hand side, we see these red dots across Australia, and that is where the Australian part of the SKA will be built. So basically, we're going to build hundreds in Africa and thousands in Australia of dishes, radio dishes and radio antennas, and link them all up electronically to make the world's best and biggest, not just radio telescope, but the world's biggest science experiment. And so what the SKA also is an idea that is several decades in the making. So for those of you who are tuning in who were born maybe in the late 90s or in this new millennium, this new century, then the idea for the SKA is older than you are, because the idea for having the Square Kilometre Array, this radio telescope that has the collecting area of 1 square kilometer, was first put on paper in the 90s. And then in the 2000s, countries started bidding to host the SKA, and this bidding process is very similar to the process to host the Olympics. So, you know, there's a lot of, you go on the campaign trail, you have a team of various experts and policymakers, politicians, and there's a lot of planning, a lot of meetings, a lot of showing off your capabilities, etc. And in 2006, 4 finalist countries were chosen: China, Argentina, Australia, and South Africa. And in that intervening time between 2006, with the finalists and the actual hosts being chosen, South Africa and Australia started building proof of concept, proof of concept instruments to show that they have the technical expertise. So South Africa built from scratch our first radio interferometer made up of 7 dishes, and I'll talk a bit more about that going forward. And in 2012, South Africa and Australia were chosen as joint hosts for this telescope. And the UK was chosen as the location for the SKA headquarters, the SKA organization, or SKAO as it's called, headquarters. And I'm here at the moment in Manchester, in northwest England, and just a bit less than an hour's drive south of Manchester is where the SKA organization's headquarters site is, on the same property, in the same area as the Charles Bank Observatory, which hosts the Lovell Radio Telescope and had just been declared in last year a World Heritage Site. So a lot of historical significance as well to where the SKAO is headquartered. Then in 2018, both SKA Precursor telescopes were completed. So these were the telescopes in South Africa and Australia that were basically the start of what the SKA is going to be, and we're going to add to these telescopes, and we've started adding in some cases to them already, to complete the phase 1 of SKA. But these precursor telescopes, which I'll talk a lot more in detail about later on, are actually, they are full and very capable and fantastic science instruments in and of themselves, and I will discuss some of the highlights of their science results later on. So ask again another question: what is the SKA? And it's a global project. So here you see a map of the world, and you see some of the partners highlighted. So the light blue countries are member countries that are part of the SKAO, the SKA organization, and that includes South Africa and Australia as hosts, the UK as the location of the headquarters, then places like Canada, India, China, several European countries are all a part of this, this organization. And then you see in pink across Africa, there are 8 African partner countries, because once South Africa was given hosting rights, we reached out to other African countries to ask them to join us in this endeavor. And the African partner countries are Ghana, Kenya, Mauritius, Madagascar, Zambia, Mozambique, Botswana, Namibia, and did I leave anything out? No, I think that's all of them. It should be 8. Botswana, Namibia, and Mozambique. Yeah. So these are the 8 African countries that will also host parts of the SKA across the continent, and have been putting a lot of effort into constructing radio telescope observatories in their own countries as well, and I'll be talking about them as well. So more technical now, what is the SKA? Something that people don't often realize when they think about these massive telescopes is that these telescopes are also big data generators. So big data is a massive buzzword and has been for a while now, and all these different kind of jobs that stem out of big data that maybe didn't exist 10, 15, 20 years ago. Data science, data scientist, data analyst, data architect, data warehousing, all these things basically to do with these large volumes of data and where to store them, how to transport them. And that takes a lot of specialized and innovative computational power and thinking. So I have two separate infographics here, courtesy of the SKA organization. The one on the left gives you some details about SKA phase 1 low frequency array, which will be extended from the SKA Precursor telescope called ASKAP. And there's a lot of information there, but the thing I want you to focus on is the square in the middle of that infographic, and that gives you some idea of the big data that I'm talking about. So in 1 second, this telescope will produce 157 terabytes of data, of raw data. And over a year, that comes to about 5 zettabytes of data. So now we're getting into this territory where the prefixes for the size of data is starting to get pretty unfamiliar. Most of us are familiar with terabytes. We're certainly familiar with gigabytes. If you're using the internet or a cell phone, you buy or you get your data in terms of gigabytes for your phone, or if you're streaming a movie or something on Netflix, something like that, you know how much that video will take up. That's also in the region of gigabytes. And so a terabyte is then 1,000 times bigger than a gigabyte. And you can think of a terabyte as often the size now of external hard drives that you use to back up your data on your computer. And so think about filling 160 of those every second. And then the SKA mid-frequency array, which will extend from the African which will be across Africa, and it will extend from the South African SKA Precursor telescope called MeerKAT, will have slightly lower rates at 2 terabytes per second and 62 exabytes per year. So just to give you an idea of these data scales, I'm going to talk a bit more about the big data aspect and the actual challenges that are faced when we're talking about data rates. And then I'm going to try and break down what zettabytes and exabytes actually mean in a more understandable way, because it is just an almost overwhelmingly huge data volume. So a lot of us will be familiar with the Large Hadron Collider that is run by CERN, and it's built mostly under Switzerland. And that's where we fire these beams of really, really tiny particles going really fast, lots of energy, and we smash them together and we see what comes out. And you might be familiar with the work that the LHC is doing from the Higgs boson discovery. They discovered the Higgs boson that was predicted to be one of the fundamental particles that make up our universe. And it recently won the Nobel Prize when Higgs won the Nobel Prize when they discovered this, and they actually found proof of this using the LHC. So currently, the Large Hadron Collider is the world's largest or biggest science experiment, and it is also a data precursor for the SKA. So I've spoken about precursor telescopes, so the telescopes that we're using as proof of concept and as sort of the idea that we're going to build out from this. So the Large Hadron Collider is the world's biggest science experiment, but in terms, compared to the SKA, it's only a data precursor. The data that's coming out of here is a stepping stone and will teach us stuff about how we're going to have to handle the SKA's data volumes. So recently, so about a year or so ago, CERN surpassed 200 petabytes of raw data collected by the Large Hadron Collider. And CERN and SKA have actually formally signed an agreement to work together to tackle exascale computing and data storage and data management. And here, I love this meme. It's based on that iconic scene in Predator, a movie that I love and talk a lot about when I do science talks as well. And basically just showing them coming together to tackle this exascale data challenge. And so let's follow that asterisk there next to exascale and talk about these data sizes. So as I said before, a terabyte is 1,000 gigabytes. So a terabyte is, I've got a 500 gig, sorry, the word just escaped me, external hard drive right here in front of me on my desk that I use to back up my desktop. And that is only half the size of what a terabyte is. And then a petabyte, which is starting to get sort of beyond the realms of what most people are familiar with in terms of data sizes, is 1,000,000 gigabytes, so 1,000 terabytes. And then exabyte is 1,000,000,000 gigabytes, or 1,000,000,000,000, yeah, it's 1,000,000,000 gigabytes. And then you even get zettabytes, which I mentioned earlier, which I said the SKA in Australia is going to get up to, and it'll be 1,000,000,000,000 gigabytes. So now taking a step back from that, just to, again, to illustrate how big these data sizes actually are. When we talk about millions, most people have this and sort of intuitive feel for is in terms of, say, house prices and things like that. When we get to billions, people often get confused, like, how big is a billion? So I'll give you an example. 1,000,000 seconds is about 11 days, but 1,000,000,000 seconds is over 30 years. So when we're going from the tera and the peta to the exa, you're going from, if you think about it in time, you're going from a week and a half to almost my entire lifetime, to about 32 years. And that's that big jump. And then when you take zeta into account, it's that another big jump. So these are the scale of the data volumes that CERN is going to help us as SKA people unpack and teach, and we're going to learn together how to deal with this, because CERN will get there as well. So just kind of have this big data in your mind, but later on in the talk, you will see how we're putting this big data and the skills that we're learning about it to good use. So here's another question. What is the SKA? It's also a driver of development. So to deal with this big data generator that the SKA is, that I've hopefully impressed upon you how massive these data volumes are, we have had to set up an organization and a way to deal with this data that we have right now from the South African SKA Precursor telescope called MeerKAT. And so the Inter-University Institute for Data-Intensive Astronomy, or IDEA, was set up. And it is the first African cloud computing data center. And it was built with its own hardware and infrastructure. So it was very purpose-built in terms of the actual physical components. And then the software was adapted from other extant software. And what's interesting about this is that the three institutions whose logos are displayed in the middle of the slide, the University of Pretoria, the University of the Western Cape, and the University of Cape Town, where I did some of my studies. So the three South African institutions, and the University of the Western Cape is actually what we call in South Africa a historically Black university, or historically Black institution, which means that it was set up as a place where non-white South Africans could go. So Black and colored South Africans, if you wanted to study at the university in Cape Town, you would go to the University of the Western Cape. And then the University of Cape Town was essentially a whites-only institution, and this was under the laws of apartheid, which only ended, in my lifetime. I was born when South Africa was still under the tyranny of apartheid. So the University of the Western Cape is one of the many success stories, and I'll come to the rest later, of the SKA. So this UWC, as we call it, or UWs, started out as a historically Black university, and so therefore, due to the laws at the time, was massively underfunded, under-resourced, and thought of as a second-rate institution. And due to the apartheid ended, and so those laws were abolished. And then with SKA coming in, the money and the resources and the expertise that was brought into the country, and especially at the University of the Western Cape, has now transformed this university to one of Africa's foremost places to study physics and astronomy. And it is now one of the leading astronomy research institutes on the continent. So this is something that happened in my lifetime before my very eyes. When I started university, I went to the University of Cape Town because the University of the Western Cape did not even have an undergraduate course in astronomy, and now it's one of the best places to study astronomy in all of Africa. So that's a classic example of the kind of impact that the SKA is having on our research institutions. So I've spoken about data, but the story's not even done. So we've built IDEA to deal with MeerKAT data, so the SKA Precursor data. But if you really want to deal with SKA data, so SKA phase 1, the much more scaled up version, IDEA isn't really set up to handle that. So we are currently busy focusing our energies on building an even bigger, more sophisticated cloud computing center platform called Ilifu, and Ilifu means cloud in one of the South African official indigenous languages. So Ilifu is going to be quite multi-purpose. It's not going to be astronomy specific. So SKA astronomy, you can see there I've got, and obviously you'll be able to do data analysis, data visualization, data analytics. And it will encourage collaborative research because this is being done in conjunction with other African countries as well, and 6 universities across the country. And then you can see I've decided to not highlight SKA astronomy on this slide, but rather to highlight bioinformatics in the top left there in pink, because Ilifu is going to be used, like I said, in a multidisciplinary way. And one of the big challenges it's going to be working on is the data analysis, storage, transportation, visualization, etc., of data from bioinformatics research. So bioinformatics has to do with the life sciences, and it's about trying to decode, for instance, a human genome, DNA, and all of that stuff. And I've just been bragging about how astronomy is so cutting edge, and we have these massive data volumes and all of that. But when we compare it to bioinformatics, actually, it's small fries. The bioinformatics information, the information that the biologists and statisticians, etc., who do bioinformatics study, that's basically locked up in each one of our cells, in our DNA, in our genome, far surpasses the information that we're going to get with the SKA. So I always say that we talk about the astronomy and SKA, and we're going to, study the universe all the way back, almost to the beginning of the universe. And it's, the universe is so vast and it seems infinite, but the data that we're going to get in that area of research is really pales in comparison to the data that you can get from every single cell in a living organism. So there is a universe outside there to explore, but the universe inside each and every one of us, in each and every one of our cells, plant cells, bacteria, etc., is really something on another scale. And it's just so incredible to think that we can work together to unlock the universe inside our bodies as well as the universe out there. So another way that the SKA has really pushed forward development in South Africa in particular, I'm going to focus on one province in South Africa in particular, and then take it wider lens to the rest of Africa. And that is by spending over 14 billion rand on construction, training, hospitality, community development, etc., in the Northern Cape province. So the Northern Cape province is the site of the SKA Precursor telescope MeerKAT, and it will be the main hub from which SKA phase 1 is built outward. And the Northern Cape is South Africa's largest province. It comprises 40% of the total land area, surface area of the country, but it only has about 2% of the population. And partly that's because the Northern Cape is mostly semi-desert or desert, which actually makes it a fantastic place to build telescopes. So both the SKA South Africa will be built out from there, and the telescope I mentioned right in the beginning, the Southern African Large Telescope with the 10-meter mirror, is also in the Northern Cape, because it has such low population density. There's not a lot of radio frequency interference and not a lot of light pollution. It's mostly sheep in that province, but it's turning out to be a fantastic boon because it means that it has the required environmental parameters for us to be able to build these really sensitive instruments there. So the SKA over the last sort of decade or so has spent 14 billion rand building these telescopes there. And just to give you some context for that, if you're not familiar with with rands and how much it really is. In 2013, so this was a few years after the SKA, after we started building these radio telescopes in particular in the Northern Cape. In 2013, the Northern Cape's GDP was about 70 billion. So this is a significant fraction of this province's overall GDP that's coming just from SKA. And that translates into about 9,000 local jobs that have been created over the last 10 years or so. More than 1,200 bursaries have been allocated just to learners, as we call school pupils, just to learners from that province, going to those schools and going out on to university. And 22 schools have direct SKA human capital development programs. So that's things like getting fully trained maths and physics teachers into the schools, where there were some schools, well, a lot of the schools did not have qualified maths and physics teachers, and that's no good. If you're thinking about not just science, but technology, engineering, and maths, you need a solid foundation in your high school. And the kind of outcomes that we're seeing are absolutely phenomenal. These are just, I didn't want to crowd the slide, so these are just some of the highlights. But another example is that some of the children who went to school in the town of Carnarvon in the Northern Cape, it's the closest town to where the telescope is, they entered a robotics competition. I think it was last year, and it was the first time that any of them had ever done any robotics or coding. And through the help of the SKA supporting them and getting them training and so on, they went abroad to the competition in South America, and they actually won one of the top prizes at this robotics competition. So this is an area that went over the past 10 years from not having anyone from their schools going to university, not having physics teachers at their schools, at the high school, so no one was really getting a science education, all the way through to winning international robotics competitions at their first try. So it just goes to show that there is such a lot of talent that is waiting to be unlocked and waiting to showcase the brilliance of African minds. We just need to be given the opportunity to do so. And through the SKA, we are getting that opportunity. And then taking a step back and looking at the continent as a whole, the SKA has also produced the first Zambian PhD astronomer, Dr. Brenda Namumba, and also the first female astronomer in Burkina Faso, Dr. Marie Kosaga. And both Dr. Brenda and Dr. Marie are fantastic advocates for science, for the SKA project, for themselves, their families, their communities, and their countries. And I've had the privilege of working with both of them, or being at the same institution as both of them. And I couldn't think of better ambassadors for this project and for science and for Black African women than these two. And it's just such a privilege to see them going from students all the way through to their postdoctoral studies right now. And it's just a shining example of what we can do if we just put the resources in the right places. So I'm going to now just quickly talk about some SKA spin-offs. So those were the direct impacts of the SKA in South Africa and Africa at large, and there are even more spin-offs from this. So the first one is called the DARA project, and DARA stands for Development in Africa with Radio Astronomy. It's a joint UK-South Africa human capital development project, and human capital development just kind of means bringing people in and upskilling them so that they have the tools and expertise to be able to tackle whatever challenges, technical challenges are facing them, their community, their country, etc. And it's driving economic development in Africa by leveraging the astronomy work that's being done across the continent. Because often what you'll find is when you work in blue sky science like I do, so blue sky science is the kind of science where it doesn't have an obvious application. So, unlike medicine or chemistry or life sciences, we're kind of just exploring to see what we can see. So astronomy and particle physics, where, we're just smashing things together and we're going to see what we can see. And people, especially in developing countries, and it's a very valid question, they often ask, why are you building telescopes? We have so many problems. Why are you spending money building telescopes? And so these spin-offs of the SKA go to show what we can do with these transferable skills that we learn looking at the stars, and how they can make life better for everyone. So a spin-off of that spin-off, or subsidiary of data of development in Africa with radio astronomy, is data big data. And here we're going looping back to the big data conversation we had earlier. Basically what data big data is working to do is taking these transferable skills of students who have been taught to be data scientists and big data scientists, big data analysts. They know how to work cloud computing, they program really well, and how to handle these big data volumes and get accurate data out of it. Taking that from astronomy into the health sphere and even into sustainable agriculture. So the same techniques, just the data sets are different. And you can immediately see how health is so important. I mean, we're living through a global pandemic right now. So having people who can deal with the vast amounts of data that can help us make better vaccines or have better responses to health crises, especially if they're global, and to address them in the particular African context, where we don't necessarily have the same resources that developed countries have. We can then build up this health infrastructure using big data to address the specific health concerns of the African continent. And then the other one is sustainable agriculture, which is also, again, incredibly important and a very pressing challenge in terms of climate change that's happening and how that, again, specifically affects the African continent. So using all of the technical expertise and applying them to different data sets in different areas and working with the experts in that area, we are building up this cohort of young African researchers who start out in astronomy, but can branch out into something a little bit more useful and more directly applicable to us, safer and more when it comes to responses to global challenges. And lastly, another spin-off is the Big Data Policy Fellowships. So this is a fellowship program for early career researchers that provides for scientists, in this case, scientists who are working in the data project, to communicate with policymakers. And it's based in the UK and started in 2018, and then 7 early career researchers that have participated so far. And then the South African Radio Astronomical Observatory done the parallel program specifically for African students, where the program based in the UK is why these policy training programs are so important. Because SKA is a global project, because there's so much money involved, because this has to have the buy-in from top politicians and policymakers, and we need to empower young scientists, especially as Africans, to be able to advocate and communicate clearly our standpoints, our needs, our desires, and make that accessible to the people who actually have the levers of power and who control the purse strings, and also to help give them and guide them in a technical sense in terms of future projects, etc. So it's really important. This is a really important and often overlooked aspect of the new way, of the modern way that science is done. It's done collaboratively, it's done globally, and that needs a lot of wrangling in terms of laws differing in different countries. And so we are empowering our African early career researchers to be able to do this and speak from ourselves, people from the communities. And this can only have good outcomes if you're upskilling people who are from the affected areas to be able to talk to policymakers, so that we know that the policies that will come out of this will be more sound and certainly have a very solid technical grounding. So now, for those of you who are just here for the science, been waiting very patiently, your time has come. Let us delve into the science. And to do that, I'm first going to introduce the current SKA workhorses, basically the 2 SKA Precursor telescopes. So the first one on the left is MeerKAT, and MeerKAT is the telescope that is in South Africa in the Northern Cape near Carnarvon, like I said. And this is a gorgeous uplit photo of one of the 64 dishes that make up the MeerKAT telescope. So these telescopes are about 13.5 meters across, and they're all linked up electronically. And in the background, you can see the beautiful night sky. Our galaxy is in the top sort of left-hand corner of this image, or the center of our galaxy, the actual Milky Way part. And if you look towards the top right, you'll see a little smudge cloud thing, and that's actually called the Large Magellanic Cloud. And I'll talk more about the Magellanic Clouds later on as well. And but further down on the right, there's a smaller smudge, and that's the Small Magellanic Cloud. And these are two galaxies that you can see if you're in the southern hemisphere and at our latitudes, where MeerKAT is and where ASKAP are in the southern hemisphere. They are up all the time. And if you go somewhere dark enough, you can actually see them with the naked eye. You don't even need binoculars. So that's really amazing. And then on the left-hand side is one of the 36 dishes that make up ASKAP, which is the Australian SKA Precursor. And in the background, you can see the Milky Way going across, and the center of the galaxy is also there in the middle. So that actually is one of the main reasons why the SKA was chosen to be in the southern hemisphere, and that is because the galactic center and the plane of the Milky Way is much more visible than in the northern hemisphere. So it's up overhead for longer, and so we can do better observations of it. And the Magellanic Clouds are actually only visible in the southern hemisphere. You can't see them in the northern hemisphere at all. And they are two of our closest galactic neighbors, and just a fantastic place to do research. And I'll tell you a little bit more about my research that links to that as well. So before I go on, I like telling these stories about how these telescopes got their name. You might be wondering. So some of you who, if you know about telescopes, you may know that astronomers can sometimes get very utilitarian when it comes to naming telescopes. We don't have a lot of creativity there. So we've got the very large radio telescope in the US. We've got the very large telescope, the VLT, as well, optical telescopes. And so MeerKAT was initially going to be called the Karoo Array telescope, because the Karoo is the area in the Northern Cape where the telescope is situated. So it was just going to be bog standard Karoo Array telescope, or CAT. And the way cat is spelled with a K there is also the Afrikaans word for cat, the animal, in Afrikaans. And so it was just going to be called CAT, Karoo Array telescope. And then something wonderful happened. Our government was able to secure extra funding for this project. And so the Karoo Array telescope, which was initially supposed to be 20 dishes, was able to expand, and now to 64 dishes. So we decided to call it MeerKAT, because Meer in Afrikaans means more. So literally our telescope is just called More Karoo Array telescope. And then ASKAP also has a funny little story behind its name. So I've been saying the word precursor all the time. But ASKAP actually stands for Australia SKA Pathfinder. And that is because it was named before the people in charge of the SKA and planning it decided to call certain things pathfinders and certain things precursors. So initially there was this plan to build these two precursor telescopes in Australia and in South Africa. And we were also using other telescopes as pathfinders, i.e. telescopes that would help us learn more about how to build the SKA. And this included telescopes in India, for instance. And so the giant meter wave telescope in Pune in India is an SKA Pathfinder. It is not going to be directly on the site where the SKA is built, unlike these two telescopes you can see here, but they are pathfinders in that we learned a lot about radio astronomy from them, and they are involved in the SKA process. And then at some point they decided that if the telescopes that are built on the site where the SKA is going to expand from, those should be called precursors to distinguish them from pathfinder telescopes. And so unfortunately, ASKAP was saddled with the wrong name. So it's called a pathfinder, but it's actually a precursor. So now on to some beautiful science pictures, which is one of the fantastic things about astronomy, is that we have these incredible images. This is an image adapted from the results of a Nature paper that was published last year. And basically what you're looking at here, when you look at it, the first thing I always see is a squid. So there's this like bubble head part, and then there's like a frilly skirt, and then there's like tendrils coming out, and there's some structure towards the bottom left-hand side, and like a long tendril going towards it. So it kind of looks like a octopus. But what you're actually looking at is the structure that you see going across the middle there, all of those bright spots, and that plane, that line there, that is the plane of, that's the center of our galaxy, that bright spot there, and that's the plane of the Milky Way. And this massive structure going up above it that's what's new. That's what's new about this. So we had no idea that there was this big bubble that was blown out in the matter and by the central black hole, Sagittarius A star of our galaxy. So that structure is hundreds of light years big, and it is indicative of a very, very energetic blast that came out of our black hole in the past and had enough force to blow out this huge bubble that we're seeing here, the remnants of it we're seeing here. So this happened a few hundred, if it's a few hundred light years big, it happened a few hundred years ago. And that's how long the light has taken, or the energy has taken to blow out this bubble. So that is extremely intriguing, because as long as we've been sort of studying the Sagittarius A star supermassive black hole at the center of our galaxy, it's been very quiet. It's very underactive and lazy compared to central black holes in other galaxies that are similar size. So now we suddenly have this insight, thanks to MeerKAT, that this black hole didn't always used to be so quiet and lazy. It was very energetic and loud, in the radio at least, in the past, and now we have proof of that. So that's opening up a whole avenue of inquiry and research for us to delve into. And this is the kind of unexpected but very exciting and very insightful scientific discoveries that we're going to be making with the SKA and its precursors. So here's another example of MeerKAT Science. This is an image that might be familiar to a lot of you. It was spread across the media and so on, and heavily publicized. And it's actually also my Twitter cover photo. And this is it's zoomed in on that area I just showed you. And you can see, if you look in the brightest part in the middle of this image, you can see it's been labeled Sagittarius A, which is roughly where the supermassive black hole at the center of our galaxy is. And you can see all these bubbles off to the left-hand side. Those are supernova remnants. So what's left after massive stars have exploded, the gas and dust that was blown out the material, and all sorts of other structures. And what you can also see here are these sort of filaments coming out, these threads, these bright filaments. And we've known about them since the 80s, or had an idea that they might be there, but this is the first time we're seeing them in such great detail, and how many of them there actually are. So this is the part of my talk where I let you in on some astronomy secrets. And one of the big secrets in astronomy is that we don't know how magnetic fields work. It's complicated to include them in your models, because when you do calculations and you add in magnetic fields, there's a lot of cross terms. It becomes non-linear very quickly. So mathematically, it's complicated, and even computationally, it's complicated. It takes a lot of time to do these computations, these calculations, and get your models right. So we often either ignore, in our first initial attempts at trying to figure things out, ignore the magnetic fields, and or add in the simplest form of magnetic field that we can to keep things as simple as possible. But that means we're obviously overlooking a massive amount of what's happening out there in the universe. And with these very sensitive instruments like the SKA precursors, we can no longer get around that. We have to start facing up to the fact that we need to get more sophisticated with our understanding of magnetism. And that's what that is exactly what the SKA is being built to do. So one of its 5 main focus areas is trying to delve into and unravel the mystery surrounding cosmic magnetism. So what is the origin of these large-scale magnetic fields and magnetic structures in galaxies? And here it is in the center of our very own galaxy. There's a lot going on, and we don't know exactly what's happening, but we're very, very excited to find out. And so lastly, just so you don't think that I am skipping over ASKAP, let me show you this beautiful false color image of the neutral hydrogen, cold hydrogen gas in the Small Magellanic Cloud. The Small Magellanic Cloud also happens to be my favorite galaxy at the moment. And that is because I will soon be working with several of my colleagues all around the world on this galaxy using both ASKAP and MeerKAT data. And I am looking for my particular type of binary stars that include neutron stars or black holes. And I'm very, very excited to get stuck into this. So here with this ASKAP image, what we're seeing is the distribution of the cold hydrogen gas, the atomic hydrogen. And what you can see here when you look at this image is on the right and on the left, on sort of the ends of the galaxy, you can see there's these voids, these bubbles. That's not an error in the image. That is actually, you can see where the gas has been blown away, either by massive stars exploding or massive stars blowing off their stellar wind, their material. Or by stars exploding. So that gives you an indication of where certain activity is happening, certain stars are, where massive stars are, etc. And then you can also see areas that are really, really bright, and that means there's a lot of this neutral hydrogen clumped up there, and that could also indicate areas of star formation. So you can see places where stars are being formed, where they're being born, and where they're dying, or they're losing massive amounts of mass. And so this is very interesting to be able to, just from looking at this one type of gas, not even the starlight or anything, you can already tell a lot about star formation and star death and their evolution just by looking at this. So the actual main thing that's really incredible and mind-blowing about this image is that using traditional telescopes, like the Australian Telescope Compact Array, which before ASKAP was built was the premier radio telescope in the Southern Hemisphere, and certainly in Australia, made up of 6 dishes, and it's been revamped, and it's really still a fantastic instrument. It would take that kind of instrument 15 months to be able to make this observation, to be able to get it to this depth and level of detail and see all these faint structures around the galaxy as well. And unfortunately, I don't have the option of asking you this, because I would have loved to be able to do some interaction or participation with the audience and ask people to guess how long they think this took with ASKAP. Because the thing with ASKAP is the 36 dishes, each of the dishes have a special set of receivers on them that when you do some electronics magic on them, they are constructed such that you can actually put them all together and you will get a field of view about 30 square degrees on the sky. And so just for context, a full moon, when you see the moon all fat and bright like that, that's half a degree in width. So 2 full moons together is a degree of arc on the sky. And so you can imagine that ASKAP is basically just this huge, sophisticated, wide-angle camera lens that has a 30 square degree area on the sky field of view. So this small galaxy fits easily into that. So because of that, because we don't have to keep moving around and going across bit by bit trying to see the whole galaxy, you get it all in one snapshot and even more. It's just been trimmed down. And so instead of taking 15 months to collect this with a traditional radio telescope setup, you can do this in 3 nights. So there's a reverse data crunch for you. Instead of going from small data to big data, it just shows you how we're going from taking almost a 1.5 years to be able to do this kind of amazing science and get the science result, and you can do it in half a week, in 3 days. So this is the way that ASKAP is revolutionizing the way we survey galaxies, and it's incredibly exciting. And we're just going to have, things are just going to be moving so fast because the turnaround time is now not in years anymore or in months, it's in days. So it's absolutely thrilling. And so this is the end of my talk. I just wanted to end with this, this closing thought, a quote from Dr. Naomi Asabre-Frimpong from Ghana. She got her PhD just a few months ago here at the University of Manchester, another incredible ambassador of astronomy and for Ghana as well. And she has this to say. She says, young scientists and graduates in Ghana are eager for this new research challenge and the SKA. The DARA program and radio astronomy have given us the perfect opportunity to show what we can offer the world. So I will leave you with that thought and that quote in your head by the amazing Dr. Asabre-Frimpong. And, you know, she speaks not only in this context for Ghana, but for the rest of Africa as well. And I hope now that you can see how things have changed so much, how the SKA has brought all of this potential that was always there to the fore. And I am incredibly grateful and proud to be associated with this project. And next time I get asked to give a talk for the RAS, if it's in a year or two, it's mostly going to have to be science, because there are going to be so many amazing science results, so many people I have to mention. And this is just the start. This is just the tip of the iceberg. And I can't wait to share with you the developments as they come in. Thank you.
Thank you, Dr. Joseph. That was brilliant. And we also look forward to hearing more about the science that the future of astronomy will bring us. Pretty impressive what you've got going on there in those parts of the world. So we do have a few questions for you. We have only a few minutes left. I think you're really happy to hear your talk. We have a couple of questions from YouTube. Remember, if you have a question for Dr. Joseph, you can put it in the Zoom Q&A box, or you can post it to, if you're following us on YouTube Live, we are streaming from there and you can post your question there. So the questions that came in from Zoom are pretty similar. So we have, they're talking about radio quiet areas, and you mentioned that SKA is wonderfully, it's built there in Africa for that reason. But these two questions talk about like Starlink, communication satellite constellations, let's see, interference of imaging by these, current projected telescopes. How is how is the SKA managing to deal with the potentials that very broadband radio frequency interference will be emanating from such constellations? Have you guys had any discussions or thoughts on that yet?
So, I mean, this was a worry right from the start. As soon as Starlink was announced, the astronomy community was very shook. We were shook, is no other way to say it. We weren't expecting that. And this is also an example of a failure of policy, I would say, and communication. So, I mean, imagine, I've just shown you some of the numbers, and everyone that's involved in making this project work only to be undone by some man who has more money than sense and just decided to put these telescopes up, or put these satellites up and interfere with our telescopes. And a week ago or so, I saw someone posted on Twitter the first Hubble image that's actually been impacted by this telescope. And I mean, the Hubble Space Telescope is the world's most famous telescope. It is our premier research space research instrument in astronomy, and we were assured that Hubble wouldn't be affected by this, and that turned out not to be the case at all. So I'm not aware of any formal talks that are happening, but certainly we as astronomers we've been trying to make our voices heard, and this kind of goes back to that point I made earlier about advocating, about training early career researchers, especially from African countries, to advocate for the research community that they come from and for the rest of the research community, and talk to policymakers and lawmakers. And since we weren't consulted as scientists, we were left out of the loop on this, and now we are facing a massive challenge in trying to mitigate all this interference. And what's also particularly galling as an African is that the reason that when you try and, for instance, on social media bring this up, you will get people saying to you, oh, well, Starlink is going to bring internet to Africa. And just based on that alone, we should be able to do this. That's more important than telescopes. And as an African, as someone who loves the internet, as an astronomer, I find this particularly galling, and it just shows the complete disregard for Africans, because we were not consulted. They didn't ask us, do you need the internet? How do you want to be linked up to the rest of the world? All of this. This person just decided, oh, I've got this money and I'm going to put these satellites in space and we'll say it's for the benefit of Africa. But there can be nothing about us without us. And this is why the SKA is so different. Because the SKA didn't just come from the outside and say, oh, this is how we're going to fix things. It's allowing us to face our own challenges and overcome them. And that is really the opposite of what Starlink is doing. And it's very disappointing. It's very frustrating. And it shows an old school mindset of how people want to interact with and help Africa, rather than the SKA way, which is coming in from the ground up and empowering people who already have the interest and the capability, but not necessarily the resources. So Starlink is a technical challenge, but it is also a policy challenge and a mindset challenge, that we need to change people's ideas of wanting to do things that they think is good for us, but they didn't even ask us if that's something we even want or need.
Yeah, I don't think you're alone in your thoughts and minds and trying to mitigate this. And it's a difficult road ahead of us, I think, with all of this, and especially important for science. And I think you're not alone here as well. You've got some SKAtelescope.org attendees, and one of them has posted a detailed SKA analysis on their website. If you go to the SKAtelescope.org website, you can look up satellite impact analysis and look more into it there. So if you're interested, I've just somewhat posted the link to the Q&A there for everyone to see.
Mm-hmm.
A couple more questions. We just have 2 minutes, so we might go a little bit over. Is that okay with you?
Yeah,
okay, great. So from YouTube, Gitu says, very inspiring, Dr. Tana Joseph. Has the presence of these state-of-the-art telescopes had an impact on the local community in terms of capturing their interest towards astronomy? So have they inspired others locally in Africa to study astronomy?
Well, locally in Africa is kind of an oxymoron, because Africa is the second largest landmass on the planet, but locally in South Africa and in the individual partner countries, absolutely. As I've said, the individual partner countries are working towards building their satellite, or not satellite, I shouldn't use that word, their local radio astronomy observatories that will be linked up electronically with the rest of the SKA and with MeerKAT as it stands. And so there's been a lot of interest, not just in the astronomy side, but obviously the technical side, construction, engineering, electronics, all of that. And what we've also seen in some countries is that telecoms companies have donated some of their old dishes that I think it happened in Kenya and possibly in Ghana, where they were given these telescopes and they were refurbished from telecommunications satellite or telecommunications ground-based dishes to working science instruments. So that's also just a different way that we're doing things, because what's nice about radio astronomy is the secret and the magic is not in the hardware. You can make a radio telescope out of a wire coat hanger or chicken wire or something. In terms of the hardware, the magic is in the electronics and the software. So we've taken some of these donated out-of-date telecommunications dishes and made them into science instruments, and that's and that takes a lot of coordination, not just from the science side, but the telecoms companies have to buy in. So there's a lot of support in that way with broader community. And of course, I highlighted the development in the Northern Cape, some of the things that have been changing. So one of the questions we often get is, if you're in this radio quiet zone, so what does that mean for the people who can't then use their cell phones and they can't have Wi-Fi routers in their homes? And the SKA, I didn't have space to put this on, but for instance, the SKA has been working with the local communities who would be affected by this to ensure that they have broadband and fiber and all this stuff. So no Wi-Fi routers, but everything's all with Ethernet cables. But they have some of the fastest internet on the continent now. So it's not as convenient as Wi-Fi, but when they do, the internet speeds that they do have are absolutely astonishing. And I'm jealous of them sitting here myself, because data is pretty expensive in South Africa as well. And I wouldn't be able to afford that if I was back home. But this is something that the SKA is enabling to ensure that these communities are not left behind when it comes to, digital needs and interacting with the rest of the world. So there's definitely a big buy-in. The students or the pupils who are at the schools are really getting top-class education now. And it is really an inspiration, because there's so many of us now. The numbers, the ranks are swelling, and our students are going out and starting their own companies like I did. They're becoming ambassadors for science, etc. So there has been a large scale buy-in from local communities, from people in the rest of South Africa and Africa. And it's just been so fun to watch it unfold.
That's fantastic. That's amazing. And I am jealous of anyone really fast internet access. That's great. And, with the world moving towards digital virtual interfaces, I mean, it sounds like with those resources, it gives also those people an opportunity to take courses that you can take from around the world, in your own home. That would be amazing opportunity. So a couple of quick questions here. Samuel from YouTube also asked, does the SKA telescopes work in tandem, parallel, and how do they optimize data gathering?
Okay, so the SKA South African telescope and the SKA Australian telescope, actually two separate telescopes. Together they are the full SKA, but the Australian telescope is what we call SKA low frequency instrument, and the one in South Africa is SKA mid-frequency instrument. So they don't work together. They're their own separate telescopes, and they work at different frequencies. But the extent of them, I mean, I've shown some images. So it will be across Western Australia and across most of the African continent. So they're already big, even though they're separate. Together they comprise the SKA. So the SKA has two components, a low frequency component and a mid frequency component. And all of the dishes and all the antennas, when they are linked up in their respective instruments, they're all connected together and work as one.
Okay, great. Is around your wonderful anecdote about how these telescopes created up, or how also over history changed the University of West Cape to be one of the first and foremost, universities in South Africa to now teach astronomy and data science. So Terry asks, are the universities in South Africa responding by offering more courses in astrophysics, engineering, and data analysis, perhaps beyond West Cape?
I mean, the Western Cape, the University of the Western Cape is just an example I use, but actually the capacity building, the human capacity building process for astronomy started long before the SKA was even, a thing in South Africa. It actually started with the Southern African Large Telescope that is run by the South African Astronomical Observatory, or SAO. And in response to us building this telescope while it was still being built, the government set up the National Astrophysics and Space Science Program, which is a program that runs, so in South Africa, our undergrad is 3 years, and then there's a fourth year, which is separate for the sciences. Other studies, areas of study work slightly differently. So you do a 3-year undergrad, a BSc, then you do a fourth year, which is a separate degree called an honors degree, and then you can do a master's and a PhD. So NASP, or the National Astrophysics and Space Science Program, was set up to train young researchers in astronomy so that there would be a cohort of locally educated and homegrown scientists who could work on this amazing 10-meter optical telescope. So NASP offers honors and master's degrees, and it was open to, certainly when I was doing it, I did my master's degree through the NASP program, I was joined by many other African students. So again, before SKA, not thinking about the 8 SKA African partner countries. So students from, my classmates were from Rwanda, Uganda, Morocco, all Africa, all that NASP still exists. And basically, if you're doing honors or master's level astronomy in South Africa, you go through the NASP pipeline. So it's expand now to just about optical, but also to be about radio. And we've had to expand it even further. So it's very what we call multi-wavelength. So the different wavelengths of light. So so you get taught about optical telescopes and optical astronomy, radio telescopes, radio astronomy, high energy, so gamma rays, because in Namibia, there is one of the world's best ground-based gamma ray telescopes. And it's called HESS, and also predates the SKA certainly. So depending on what you want to specialize, we've sort of expanded NASP to take this all in, and this pipeline has been running, or this program has been running since the early 2000s, so just before I started university. And one of the countries, African countries, that's also had started sending NASP students more than 10 years ago, or sending students to NASP is Madagascar. There are many NASP graduates from Madagascar who are now early career researchers doing postdocs all around the world, and also helping to grow the scientific community in their country. And it's just been amazing to see. And it's just always fun meeting up with, we call ourselves NASPies, from different countries. You hear different accents and different languages, and just such a wide variety of science even. And it's just really fun to see. So yes, so NASP was set up in anticipation of needing a workforce for the optical telescope, and then it came in very handy when we also built the radio telescope.
Well, we definitely look forward to a more diverse workforce in astronomy. And thank you so much, Dr. Joseph, for sharing with us the future of astronomy with the Square Kilometre Array. It was fantastic to have you. Would you like to say any last words?
Yeah, I just wanted to say thank you for tuning in, and thanks for the fun questions. I hope this was informative, and I hope you had a good time as well. And enjoy the rest of your evening, and good night to my any compatriots tuning in from South Africa, because you're 2 hours ahead, so it's after 9 p.m. So I guess, yeah, good night to you, and good evening to those of us who aren't in such late time zones. Goodbye.
Hi, well, it was wonderful having you. And if you would like to have some more experience with astronomy, this weekend, the 14th of November, Saturday, we're beginning National Astronomy Week here in the United Kingdom, which is the Mars Encounter. If you haven't noticed yet, Mars is beautiful and bright in our night sky, and we would love for you to come and join us. So we're going to be having talks and activities for kids. You can go to Eventbrite and search NAW 2020, or go to astronomyweek.org. And again, we thank Dr. Joseph for being with us, and we'll see you again soon. Have a good evening, everyone.